As Dan has presented, the evolution of data management and data usage is driving it from what was traditionally just storage and search, which is not much more than the historic digitalization of paper processes, through now to intelligent, connected and automated systems. And this requires a number of different things. You need high quality authoritative data, but you also need automated data integration and synchronization between systems. And then you need communication to happen between the different systems to make use of that data. What's important is it doesn't mean that all this data needs to be managed in a single system, and you can acknowledge that these disparate systems can remain separate, either within an organization or between organizations. It just means that the different aspects of the related data will be mastered by different groups. As you can see from this graph, the higher value applications further up the line require more rigorous data management and more automation in order to unlock their potential. As you may have seen on Monday's plenary presentations, One Spatial technology enables location master data management using automated rules to measure and improve data quality and consistency. And this is both for use internally within an organization, but just as importantly, when matching data between organizations to cross-reference it or link it to the authoritative source. And from that, you can start to build semantic meanings between the data sets. The One Integrate rules engine is complemented by the Data Gateway portal, and that provides controlled access to authorized users to run rules using an easy-to-use interface for uploading data. And that can be used for a number of data automation rule use cases, such as data validation, data improvement and enhancement, or data acceptance and ingest. One Data Gateway allows administrators to grant users access to different sets of rules. And this allows monitoring and analytics on the uploads that are made, tracking data quality over time and reporting on hotspots such as which rules cause the most problems or who are the most prolific submitters of the data. Here's an example of a location master data management architecture using this approach. Here there is a central enterprise store of authoritative data, but importantly this is just one of many sources, each of which masters a different aspect of the same real-world phenomena. At the top, Data Gateway is providing cloud access to rules-based apps, such as positional accuracy improvement or PAI. This improves the location of provided data based on shifts that are calculated or inferred from authoritative data. And then there's data ingest, so that's for example to receive external data, then you can validate it, and if it's correct, integrate it into a central store. And then there's address matching and there's 3D integration, and we'll see some examples of those in a moment. Now these allow cloud-based access to the capabilities which depend upon or sometimes even augment that core enterprise data. At the same time, there is integration with external systems. So this might be the data services that are accessed on demand in order to provide reference data for the Data Gateway apps, such as Ordnance Survey Data Hub. But these external systems might also be running rules via the APIs, or accessing either the core data or even the dashboard statistics for analytics insights. This is an example of a Data Gateway user uploading data to an app. In this example, it's a police records management file which requires its UPRNs to be corrected. UPRNs are unique property reference numbers that represent real-world addresses, and they need to be correct in order to enable data sharing and analytics. When the data is uploaded, then first checks that it's uploaded in the correct format, and then it accesses appropriate reference data in order to run rules on it. And there are 3 stages. First, it runs One Integrate rules to check whether the UPRN addresses can be correctly matched to the authoritative source, and provides a data quality score, in this case 23%. Then it runs enhancement rules to improve the submitted data. Then finally it validates the data again, and this time we can see that the data will have been improved. In this case, 73% now. So once completed, the user can now download a summary report and also download the now improved data. All of this activity has been recorded for users and administrators to view dashboards about who did what and when. And here's the final report that tells us what happened, and the user can also download the now corrected data and upload it into their own systems. Finally, I'd like to show you One Integrate. OneIntegrate is OneSpatial's rules engine, and rules do one of two things. They either validate the data, so you write rules and you run it against the data and it tells you where your data does not meet the rules, but you also use it to improve data, enhance it. And that's either to fix problems, to integrate different sources of data, to improve, infer, and generate some sort of improved integrated result. This is a OneIntegrate session. A session is a series of tasks, so it opens data from one or multiple sources, and then it runs a number of rules. So each of these steps is a separate rule run. Where it's a validation rule, then you can see each rule has got a name. Each rule has a definition, so the rules are defined using a user interface so that data experts can write the rules. You don't have to have a programmer to write them. And where it's a validation rule, then there's a conformance result on the right hand side, so we can keep track of this validation quality over time. And as well as all the summary reports, there are detailed drill down information about which features have failed and why and where. So let's have a look at some of this data. This data is from Ordnance Survey Northern Ireland. So we've got 2D data, so the 2D building footprints in orange there, and in green we've got the 3D buildings. The 3D buildings come from a number of different sources, so some of them will have been originally extruded up from the 2D buildings, some of them will have come from, say, CAD files, or some of them will have been created using LiDAR scans, and that gives things like the pitch of the roofs. And we can see there's a general correspondence, so things sort of look right, things are in the right place. And on the right hand side we can see the results of all of the various validation processes that have been done. So each of these validation reports, which can be downloaded as a GIS file or an XML file, we can have a preview of them here. This is using OneIntegrate's map viewer, which is as a preview of your validation results. It's something you use while you're building up your validation rules. So let's step through some of these. So this is a rule where we said, okay, well, we expect our 2D buildings and our 3D buildings to match exactly. If you collapse the building into 2D, it should exactly match the building underneath it. And actually we found there are 0 buildings that meet that requirement. And that's because of the subtleties of the encoding. So there will always be subtle differences. So we said, okay, let's be a bit more generous. Let's say if they're within a 30 centimeters, then we'll accept that. So show me all the differences where there is greater than 30 centimeter mismatch between the 2D buildings and the 3D buildings. And that still were quite a few. And then we said, okay, well, what about 1 meter? So let's look at the big differences, 1 meter differences between the buildings. And we can see with these markers, these are all differences between the buildings. Some are different because of positional offsets. So the data is positionally in the different place. Here is a temporal difference. So this is real world change. So at some point, these 2D buildings have been knocked down and replaced by a new building, a clinic or something. And the 3D data is more up to date, and we can see the 3D data contains that, but the 2D data doesn't. This is an example of positional offset. Some of them are more to do with the subtle encoding. If we just turn the perspective off, you can see there are details in the 2D building that aren't present in the 3D building. So that's a difference in the encoding of how the geometries were captured and the level of details required. So we've got a view of the validation results for the data, and we can step through these non-conformances. Now, some of them are because of positional mismatches, so that's something we want to address now. Is there a way of automatically improving the data based on the positional location? Now, in this case, we know that the 3D data is more positionally accurate, and that's because it's come from sensors and it's come more recently. And we can see there's a mismatch between fairly clean mismatch between this 3D building and the 2D objects underneath it. And there's also a difference in the encoding. So if I select these 3 buildings in 2D, they're all captured as a separate geometry in 2D, but in 3D that's one big structure. So visually we can see that they correspond, but even the structures, there's not a clear one-to-one mapping. And so what we want to do is create rules that despite these differences, we can offset the 2D data to match the 3D data. And we can use rules in OneIntegrate to do that. We can generate shift vectors by clustering the 2D buildings that touch, generate a shape that's equivalent in size and area to the 3D buildings once you've collapsed those, and automatically generate shift vectors. You can see these shift vectors there that say, well, that is the correspondence. And you can also see the points just to the north of that. Those points say these things do not shift. So it's very important that we only shift the things that need to shift. And after the automatic shift in one integrate, you can see now, and if I step between them, you can see the data being shifted so that the 2D buildings are now directly underneath the 3D. And we can prove that because we've got a validation rule that looks for the conformance of the data. And after having shifted it, the conformance goes from a lower conformance to a higher conformance. And that's proof that that positional accuracy has been updated. So that's one example of a type of mismatch between the data. Now there's another use case that I'd like to show here. So if we turn the perspective on again, and this is about generating floors within buildings. So often the use cases we see for 3D data are things like, for example, taxation or environmental analysis. What's the heat loss of this type of building? How efficient is it? And for some of these tasks, we want different floors or even sometimes different rooms within a building to be generated. And that's something that, again, we can do automatically with the rules. So we can have a look at the buildings and say, well, that's this building, the 2D footprint has information whether it's commercial or residential. And some of them have information about how many floors are in there. So for example, these are residential buildings. And if there isn't information about how many floors, then we can infer that because a residential building will typically have roughly 3-meter floor heights. So what we want to do is calculate, and we've got information about the roofs as well, so we can work out what is the space between the bottom of the roof and the ground. How many floors can we fit in if they're approximately 3 meters high for a residential building? The other buildings there behind us are commercial, and so they will typically either have number of floors stored, or they will have we'll assume a 3-meter building. And also we can see there's a different in the residential buildings there is a different structure. So we want to split up not just by floor but also by property based on the underlying 2D data. And one of the buildings here also has, rather than just using the 2D footprints, then there are floor plans we can use, and those floor plans can be used to split up not just individual floors but also individual rooms within a building, because those floor plans are available. So if we turn off the roof surfaces, so we can turn on the internal floors that have been generated by the rules. These are entire floors because we only have the footprint for the building, but this building we've got the floor plans. If we just turn those floor plans on, then those floor plans can be taken, and each floor plan knows what floor it represents, and we can split this building up not just into floors but into separate apartments or separate rooms within the 3D building. So here we're enhancing the 3D data based on the 2D data. So what we've seen is one spatial software being used to achieve automation using rules, and that automation is a vital part of data management, and that data management is what moves us up the path from simple data storage through to knowledge management and semantic integration between systems. Thank you very much.